so you're in your own notebooks today. We're going to go, I don't want to say we're going to go very quickly, but there's going to be a lot of stuff. And today, at the beginning, we're going to pick up where we left off yesterday, but then we're going to teach you something that's brand spanking new. Probably you've never seen it before in your life. Okay? So that's going to be today. So we're going to teach you something brand new for you. Okay? All right? Here we go. So we finished yesterday with that function. We all came up with that function for the population growth of San Jose and from 1990 to, or based off of the data from 1990 to 2000. Right? Okay? So a couple of things coming out of that one. So what is T in this function? T is time in years since 1990, right? Okay. So T in this equation is time in years since 1990. That's important. Okay. And our outputs, okay, what we get out of when we put stuff into this function, those are going to be in, if you were in my class, they're in thousands. Okay. If you had Schmeling, I think Schmeling actually put in 782,000 and 895,000 and all that stuff. But for me, they're in the thousands. Okay. So we have to multiply by 1,000 at the end to get, if we, like for instance, in letter C here, according to the model, what would the approximate population be in the year 2005? Well, that means I'm going to find P of what? 15. I need to find P of 15 here. So I need to plug in 15 into that function. Anybody? When I plug in this on mine, I get 957.4832306, right? But what do I got to do that to find the actual population? Multiply by 1,000, remove the decimal point to the right 3 spots. Okay? What about the 0.2306 then after that? What? Round. So chop it off? Be the same? Yep. Because we can't have 0.2306 of a person. So this would be 957,483 people living in San Jose. Yes? Okay. Now, what we're going to do is now we're going to sketch a graph of, I don't want to do that. See, this is the problem. I got to come over here, and I don't have a slider, so I can't. So now I want to sketch a graph of this function. Okay. Is it a growth or is it a decay? Growth, okay, because population is growing. Says so by that one that we just found. So it's going to look like math, correct? Give me one point that it goes through. 0,782. Another point that it would go through would be 10,895, right? Okay, right? It also said that we should label our axes with words. Okay? So horizontal like, what would the label be for our horizontal? Very good. Yep. Years since 1990. Okay. Vertically, what would our label be? Population of San Jose? In thousands. Yep. I would hope it would be in people. Okay. So population in thousands. Okay. Good stuff. Love this stuff. Okay. Lastly, what we would like you to do is, assuming that the population continues to grow, we want to figure out when it hits 1 million people. I'm going to do that. We did have, right now, we haven't refreshed your memory as to how to solve with logs. So we're not going to have you solve this one with logs right now. So we're going to solve it graphically. So I'm just going to put the graph up here, and then I'm going to have you guys basically tell me what I need to do to make it be what it is to be. Okay? So first off, we need to start with our function. Agree with me that that is our function. Okay? All right? When I hit enter, what's the problem? Can't see it, right? Okay? So give me a possible solution that I could use to see the graph. We could adjust our axes, or we could zoom out. Okay? Which one do you think is going to be quicker? Probably adjusting the axis, because we got to zoom all the way out to 782, right? Okay, so that might not be the fastest. Okay, so we're going to go back here into menu, window and zoom, and we're going to go under window settings. Now, let's think some logic here. We said that our X values was years since 1990. Yes? Okay. So can it be negative? Yeah. Because were there years before 1990? Yeah. And were there people living in San Jose at that time? Yeah. So it could be. Does it pertain to what we want? No. So it really doesn't matter to us with that. So I'm going to leave that at negative 10. Okay? What are we thinking to get to 1 million? How many years do you think? Just out of curiosity. Yes. 20? Okay, which means I'd have to go out to 20 years, right? Okay. Just to be safe, I'm going to go 25. Our y's. What was our y's on our graph? What was the y value on the graph that you just drew? What was the y's? Words. Population, right? Do I need negative? No. No, don't need negative there. I'm going to go, now you'll find that I'm a fan of being able to see my axes on my graph, so that's why I went with negative 100 there. You'll see why here in a minute. Okay. What do I need to get up at least to? 1,000, right? Because we're in thousands, right? We're population in thousands, and 1,000,000 is 1,000 thousands, right? So what do you want to go? Something, give me a number above 1,000. 1,200. Okay. So there's just a snippet of our graph. Yes? Okay, that's our population. We want that to be equal to 1,000,000, right? So I'm going to put in a second function. What's my second function going to be? Y equals 1,000, yep. Just straight up 1,000. There it is. Now what am I going to be looking for here? The intersection point, yep. So that's a menu, and analyze the graph, in intersection, and there is my intersection point. Now, the kicker here is I want you to tell me, I want you to interpret what this actually means. While I dump it into where did it go? Oh. It must not have captured. What does that actually mean? There it goes. When does the population of San Jose reach 1,000,000 people? Whenabouts in 2008? Early 2008, late 2008, middle 2008? Early? End of February-ish, maybe? Yeah. I would say probably in February of 2008. Okay? Because the intersection point happened at 18 years, which remember was 18 years after 1990. So that puts it in 2008. And the 0.219, can we have 0.2 of a year? Yeah, that's where the February part comes from. Okay? Good times. What I would like you to do now is, I'm not going to have you solve this one to figure out when it's 1,000,000 people, because you guys don't have the graphing calculators right now, and I didn't get them out for you today because I just didn't want to have them out for like 5 minutes and then put them away. Okay? But I want you to come up with the exponential model for Madison's population. Okay? Go. I switched those points around, okay, to make so my function is going to be, T is going to be in years since 2010. Okay? So if that's the case, then 404 is my initial value, because it's my value at T equals 0. So then my function, P of T, would be equal to 404 times B to the T power. utilizing my second data point then, I would say that 487 is equal to 404 b to the 10th power, dividing both sides by 404. And then taking the 10th root. So my function here would be and I think we did it in the last class, but I think it ends up being 2058, late June, early July of 2058 is when it would go over that, but I'm not worried about that right now. Okay? Agree? Love it. Try this one. Now, find me what the value of my 6210R tractor is in 14 years. TL, that's what that tractor is right there. Currently in the shed in my farms. True story. Oops, I threw my calculator on first. 0.95 raised to the 14th power gives me that. Times 192,000 gets me, I get 93,633.60. Concur? Yes? You did what? Okay. Okay. Love it. All right. Now, let's talk brand spanking new. All new stuff here now. Love it. Okay? So, we've been talking exponentials last couple of days. Yeah. Okay. What's the problem with an unchecked exponential growth? For instance, let's talk San Jose again. Okay? San Jose's population, we found, was growing exponentially. Yes? Okay? What's the problem if San Jose's population continues to grow exponentially?
It's going to be a growth proportion.
Like, what do you mean?
It's going to be way bigger than it should be in the company.
So, like, there's going to be too many people for the space that is allotted for San Jose?
Yeah.
Yeah. Okay. And realistically, with, did you have one, Jim?
Oh, I was just going to say, people, it grows at a rate, but it doesn't stay at 5%.
So it's growing, and so the more years we get, the faster it's actually going to grow. Yeah. So San Jose is going to run out of space, right? Okay. So sometimes it's not always realistic to model with an exponential function. Okay? You know, a plant or a tree, you know, the crops on Linsmeyer Farms, they get a little bit of heat, they start growing exponentially. Okay? But there's a limit to their growth. Okay? My bean plants only really get to be maybe 2 feet tall. Okay? And that's in a really good year. Okay? Corn, typically, corn usually gets about 12, 13 feet tall. Okay? On a good year. Okay? Population of a city won't grow forever. Sales of a new product might start out exponentially, but it can't sustain that growth pattern. Okay? So for those situations where growth begins in an exponential manner, but eventually it's going to slow down and level off, we have this function called a logistic function. Okay? A logistic function looks like an exponential function up to a point, and then it says, tap the brakes. And it slows down, and it levels off. And it stays there. Okay? There are two key parts to a logistic function. The first key part is all logistic functions have a horizontal asymptote at y equals 0. All of them. Okay. The other key part to a logistic function is they have a second horizontal asymptote, an upper bound, if you will, that we call the limit to growth. Later on, we're just going to call it y equals c. Okay? So it's got, and it's that the entire function lives in between those two horizontal asymptotes. Never gets out on above, never gets out on below. Okay? Now, this one that I label or that I drew for you here, that is a logistical growth because it's growing at the start. There's also a logistical decay, which would start up at the upper boundary, and then it would decay down, and it would end along the lower boundary. Okay? So there is a growth and a decay for a logistic function. Okay? How we determine those, so here, these two over here, are the two different forms of a logistic function, depending upon if it's an e, a base e, or a regular base exponential. Because we got to have that exponential growth to start. So the way that you go about determining if it's a logistical growth or logistical decay function is based off of this exponential part in the denominator. Okay? That's going to tell you growth or decay of your logistic function. And it's a reverse thinking. If it's an exponential decay in the denominator, then it's a logistical growth. Okay? It's a reverse relationship. So it's a growth if B is between 0 and 1. That makes it a logistical growth because that's an exponential decay in the denominator. If K is negative, that makes it a logistical growth. A logistical decay then would have b greater than 1, and it would have k being positive. Okay. Let's put these to work. Let's make some logistic functions. Okay. So, here's a scenario. This logistic function has an initial value of 12, which means it has a y-intercept of 12, which means it goes to the point 0, 12. It has a limit to growth of 60, and it passes through the point 1, 24. Okay? We want to come up with a logistic function. So, we want our function to look like y equals c over 1 plus a b to the x power. From the given information, do I know any of those values, a, b, or c? Izzy, what do we got? What's a? It is not. I hate to be the bearer of bad news. That is not the one that we know. What's c? C is 60. That's the only one that we know. Okay? Because the limit to growth is that c value, and that makes this be 60. Okay? So we know that. Now, let's use this point, my y-intercept of my logistic function, Izzy, if it were just a straight up, I forgot to finish what I was saying to you. If it were a straight up exponential function, then yes, a would have been 12. But we want the a value in the logistic function. So that's why it's a no. Okay? So if we want to do that, so now my y value is 12. 60 is still 60. 1 plus, I don't know what a is, I don't know what b is, but what is x? X is 0. Ooh, that's kind of helpful, isn't it? Okay, why is x being 0 helpful? Because what? So that b to the 0 is 1, right? Okay, so that's really gone, right? Because 1 times a is just a. So then this one can go like that, right? How am I going to solve that now? Multiply both sides by 1 plus a? Yeah. Then what? Could distribute, or I could just divide by 12. And then subtract 1 gives me a is 4. Right? Okay, so now we've got a and c. Now we just got to find b. So now I'm going to utilize this other point that I go through. It gave me this other point that it went through. So I'm going to utilize it. And I'm going to say now 24 is equal to 60 divided by 1 plus my A value is now 4. And that's going to be B to the first power then, right? Okay. What can we do there then? Same thing, right? Multiply by 1 plus 4b. Divide both sides by 24. Subtract 1. Dividing by 4 is the same as multiplying by 1/4. So then that would give me B here is 3/8. Now I've got everything that I need. My function is going to be y equals 60 divided by 1 plus 4 times 3/8 to the x power. Questions, comments, concerns, clarifications? You try one. So I got an A value of 5. Yes. I got a B value of the cube root of 1/5. Yes. Which gives me a logistical function then of y equals 30 over 1 plus 5 times the third root. Oops, that's a bad 3. Doesn't even look like a 3. We'll just start over from the 5. To the x power. Agree with that? Love it. Okay? So, want to just do some quick sketches here of what's going on with this particular function. Okay? So my first question is this. Is this a logistic function or is this an exponential function? Logistic, because it's got the fraction in it, right? Okay. Is it a logistic growth or a logistic decay function? Growth, because it's an exponential decay in the denominator. I would concur with that. So how I would go about drawing this graph is all of your logistic functions are going to be, or all of your logistic growth functions, I should say, are going to look like that. That's what they all look like. So start with it. Okay. Now, what can we add in to that graph? Which ones? Y equals 0, and Seamus, what's the other one? What is the limit to growth? 8, so it'll be y equals 8. Love it. Okay. So add in your two asymptotes. I always like to label my asymptotes also. Okay. And what's the easy one to find? Or what's the easy point to find, I should say? Sorry, I should have said easy. I forgot to say point after what's easy to find. What is it? Y-intercept. How do I find the y-intercept on any function? Plug in 0 for x, right? Okay. 0.7 to the 0 power is 1. Times 3 is 3. Plus 1 is 4. 8 divided by 4 is 2. So this goes through the point 0, comma 2. That's it. That's the easy ones to do for that one. Okay? So, with that being said, what I would like you to do now is I would like you to do the same on this one. So I want you to graph it, and then find me the y-intercept. Logistical growth or logistical decay? Growth, because the exponential is a decay, right? Or the exponential part, I should say, is a decay. So it's logistical growth. So start with it. Add in your asymptotes. Asymptote location is y equals 0 and y equals 20. Love it. Okay. Y-intercept, then, plug in 0. Negative 3 times 0. 0, e to the 0. 1 times 2. 2 plus 1. 3. 20 divided by 3 is... What?
6 1/3.
Oh, 20/3 is so much prettier. It's like me, pretty. Okay? Alright? So, I handed out a thick homework packet for you. Okay? What did you, there's a lot of papers in there. Yeah. Okay? We killed some trees on this packet. Okay? As of right now, listen up. This is important. As of right now, if you wanted to get a jump start on that homework packet, you can do front and back of the first page and front and back of the second page. So you can do the first 4 sides as of right now. Okay? First 4 sides. Testing. Homework is always due testing. As of right now, the test is scheduled for Thursday, October 3rd.